Hey class, what's up? Happy Friday. In this video, we are going to be introducing polynomial and rational functions. So starting off with complex numbers, and we're going to ultimately end up seeing how those complex numbers play into quadratics and other rational functions, such as x to the fourth and x to the third. Okay, so leading us off, here are 5 objectives that we are going to cover within this video. So hopefully you can follow along. Go ahead, pause and stop whenever you need to get caught up on your notes, but you should be writing along so you have something to reference back to. The imaginary unit I is one that I know Algebra 2 teachers talked about a little bit at least, so I'm hoping that you'll kind of remember as we go throughout this video. So what I want to point out to you is this, that remember I represents the square root of a -1, and therefore I squared represents -1. Well, how does that work? Well, if we take I and we square it, that means that we are going to be squaring the square root of -1. Well, squaring a square root undoes the square root. So they basically, here I want to take a marker. They basically cancel each other out. Okay, they undo each other. So that is why I squared becomes -1. Now, I want you to remember what I and I squared represent because of the fact that they are going to show up the most common. So if you can just remember, oh, Ms. Baden, I squared is -1, it'll help with a lot of our classwork. Imaginary unit I is just part of the complex numbers. So here is what a complex number actually looks like. The BI is your imaginary part, where the A is your real part. Those are the numbers that you actually will find out in the real world. And the imaginary part, well, you all had your imaginary friends at one point. Okay? Now, when it comes to conjugates, now this I know Algebra 2 did not teach you. So please write this down. Okay? Conjugates. We're going to use conjugates when we are dividing 2 complex numbers together. And really the only thing that you need to know is that a conjugate takes one complex numbers and makes it the opposite, but only changing the symbol that is in front of the imaginary unit. Okay, so I'm changing that plus BI to become a minus BI. Well, let's get started with our basic operations. Well, when you were in 1st and 2nd grade, you started with adding and subtracting. So that's exactly what we're going to do here. Now, what you have to remember is it's kind of like combining like terms. You have to combine your whole numbers together, your real numbers together, versus your imaginary numbers or your variables together. Okay? So when we take a look at this first adding question, I have a real number 5 and a real number 7. Remember, I'm adding, so I'm going to take 5 plus 7 and get 12. Well, now I have my imaginary units. Again, I'm adding those together. So -11i plus 4i is going to give me a -7i. So my real answer would be 12 minus 7i. Remember to always write the real number in front and the imaginary unit at the end. Changing it up a little bit, we have that minus sign. Well, what we're going to do is we're going to go ahead and distribute that minus sign, making this second complex number become the opposite of what it actually is. So our new problem is going to say -5 plus I plus 11. And then the opposite of -6i is going to be plus 6i. I'm going to go ahead and combine my like terms together. So -5 plus 11 is positive 6. and then I'm going to take my I plus 6I, and therefore I get 7I. That's my final answer. Again, using that whole idea of distributing, I'm going to distribute that 4I out in front to the remaining terms inside of the parentheses. In doing so, you're just going to multiply it through as if it were just any other number, like a 3x or something like that. So 4I times 3 is 12I. 4I times negative 5I is a negative 20, because the 4 times the negative 5, and then I times I is I squared. I told you that I squared is going to come up a lot. So remember that I squared is the same thing as negative 1. So really, what is my problem saying? 12I minus 20 times negative 1. Well, I can simplify this part further and say that that's a positive 20. 12I plus 20 then becomes my final answer. In completing this next part, some of you might multiply this using the FOIL method. I like the generic rectangle, so that's what I'm going to do to complete this problem. So I'm going to place my products on the outside, so 7 and negative 3I, negative 2 and negative 5I. All right, now I'm going to multiply them together to get the interior. So negative 2 times 7 is negative 14. 7 times negative 5I is negative 35I. Negative 2 times negative 3I is positive 6I. Negative 3 times negative 5 is a positive 15. And then I times I is I squared. Again, remember, what does I squared really mean? I squared is negative 1. So 15 times negative 1, that upper right box really is saying negative 15. So if I go ahead and combine my like terms together, I'm going to start with my real part, which is the negative 14 and the negative 15, combining them to give me a negative 29. Now my imaginary parts, negative 35I plus 6I is going to give me a negative 29I. That being my final answer. My next example, whoops, too far. My next example is going to involve dividing two complex numbers together. And in doing so, you really need to multiply by the conjugate. Well, when I multiply by the conjugate, remember that it's really only changing the symbol in front of the imaginary unit. So I'm going to multiply the numerator by 2 plus 5I, multiply the denominator by 2 plus 5I. Notice how I'm only referencing the denominator. The numerator, the 7 plus 4I, is just going to stay 7 plus 4I, and I'm not going to do anything with it. Okay? When you multiply two fractions together, remember you multiply them straight across. So really what I have is 7 plus 4 4I times 2 plus 5I in the numerator. And now in the denominator, I have 2 minus 5I times 2 plus 5I. Well, what happens is I'm going to have to make two generic rectangles, one for the numerator and one for the denominator. Placing my products on the outside, and then again, multiplying to get the interior. Again, here I have 5 times 4, which is 20, but I times I is I squared, and remember I squared is negative 1. So really I have 5 times 4, so 20 times negative 1 is a negative 20. I have another generic rectangle I need to make for the denominator. 2 minus 5i times 2 plus 5i. Multiply there to get the interior. 4, 10i, negative 10i, and then negative 25i squared. Okay, I told you that I squared is going to come up a lot. So really, that upper right box is saying a positive 25, because that I squared is negative 1. Now I'm ready to combine my like terms and put my final answer together. So in my numerator, I have 14 plus negative 20. Remember, real part always comes first. So negative 6. 35i plus 8i is going to say positive, what is that, 43? 43i. My denominator, well, the 10i and the negative 10i are going to cancel each other out. Now, all I have left is 4 and the 25, leaving me with a denominator of 29. Here we have another set of operations that we need to do with square roots of negative numbers that involve I. Okay. Well, when we look at this, it's really important that you take a look at that notation that you see in the red box. Okay. So write that down. Really, what this notation is saying is that you can just exchange the negative and pull out and make it an I. All right. And that's what we're going to do with all of these examples. Now, you might say that this first example equals the square root of 100, taking the negative 24 times the negative 25 times the negative 4. Well, that simply is not the answer, okay? You can't just do that. Not with complex numbers anyways, not with our imaginary unit I. What we need to do first is pull out that negative, making it I times the square root of 25 times I times the square root of 4, just following that notation that we have in the blue and the red box. Now, I can take the square root of 25, which is 5, and make it 5i, times the square root of 4, which is 2, making that 2i, multiplying those two numbers together to get 10i squared. I squared is negative 1, so 10 times negative 1. My final answer is negative 10, not the square root of 100, giving me a positive 10. Now that same idea goes with adding and subtracting negative radicals. Okay, so in this example, we're going to do the same thing. Pull out that negative, making it an I. So I have this I times the square root of 18 minus I times the square root of 8. However, in this example, 18 and 8, they're not perfect squares like 25 and 4 were. However, we can modify them to find a perfect square. Well, what I mean is I times the square root of 18. Well, I can change that 18 to be 9 times 2, right? 9 times 2 is 18. I can do the same thing with 8, making it I times the square root of 4. Whoops, let's get rid of that. Making it 4 times 2. Now, why am I picking these examples? Like, why didn't I pick 3 times 6 to give me 18, or 2 or 1 times 18? The reason why I picked these two factors of the above numbers is because 9 is a perfect square, and so is 4. So now I can take the square root of 9, and that's going to give me 3. So 3i times the square root of 2. I can do the same thing with the 4, take the square root of 4, and that's going to give me 2i times the square root of 2. Okay. Now, the reason why I'm doing this is because when you are adding or subtracting with radicals, these numbers that are inside of the radical symbol have to be the same in order to perform those operations. So since 3i times the square root of 2 minus 2i times the square root of 2. Since the square root of 2 and the square root of 2 are the same, I can actually perform the subtraction. With like terms, 3i minus 2i is I. Square root of 2 minus square root of 2, well, that just happens to still be the square root of 2. Okay, you don't actually perform that subtraction with those. Okay, so that makes my final answer I times the square root of 2. Well, let's take a look at this example. Okay, again, we're involving radicals with negative numbers. When I go to simplify this problem, I want to first rewrite it as negative 1 plus I times the square root of 5, following that same example that we did in the first two problems, making that negative come out and turning it into an I. Now, we're going to go ahead and make our generic rectangle. Negative 1 times I times the square root of 5, negative 1, I times the square root of 5. Oops. Hopefully that will be okay for you. Negative 1 times negative 1 is a positive 1. Negative 1 times I times the square root of 5 is just going to make that I negative out front and do nothing with the square root of 5. Again, that's going to be the same thing in the upper left-hand corner where I take the negative 1 times I square root of 5. So it's going to become a negative I square root of 5. And in the upper right-hand corner, we're going to have I squared, because I times I is I squared. And the square root of 5 times the square root of 5 is the square root of 25, which is 5. Okay, so you can write that I squared times the square root of 25 and simplify it when we go down for our final answer. So I have 1. Where did that extra dot come from? Okay, so I have 1, and then I have 2 negative i's times the square root of 5. Then I have this I squared, square root of 25. So I squared is negative 1, and the square root of 25 is 5. So negative 1 times the square root of 25 is a negative 5. When I simplify that even further, my final answer is going to be negative 4 minus 2i times the square root of 5. After combining like terms. Now take a look at this next example, okay? Looks pretty complex, but really it's not that difficult. If you take a look at it, the first thing we're going to do is turn that radical to be I times the square root of 50. Okay, we don't really like working with those negative radicals over 15. Well, square root of 50 is not a perfect square, but like I said before, we can modify it. So it's going to say negative 25 plus I times, well, what two numbers multiply to 50, and one of them being a perfect square? The answer is 25 and 2. So I can take the square root of 25 and bring that number out. So what I'm going to end up with when I do so is negative 25 plus the square root of 25, which is 5, so I have 5i times the square root of 2, divided by 15. Wake up! Okay, after doing so, there's a lot of multiples of 5, so we're going to reduce everything by 5. Okay, negative 25 can be reduced by 5, 5 can be reduced by 5, 15 can be reduced by 5. All right, so when we factor a 5 out, I get 5 times negative 5 plus I, square root of 2, and then divided by 15 still. Now that 5 and 15 can be reduced. So I'm going to cross off that 5, and this 15 becomes a 3. Reducing my fractions, that's all I just did right there. So my final answer is going to say this. I'm going to write it in the upper right-hand corner where I have a little bit more room. negative 5 plus I times the square root of 2 divided by 3. This right here in green is my final answer. Our last one, ladies and gentlemen. Yay! Okay, our final example. Thank you for watching this video this long. Okay, stop and pause if you need to. Solving quadratic equations with complex imaginary solutions. Oh my goodness, right? So let's just first off and figure out if it's even factorable. Well, 3 times 4 is 12 and negative 2. What two numbers multiply to 12 and add to negative 2? Last time I checked, there wasn't a solution. Okay? If you find one, let me know. But I am not there yet. Okay? So, when we go to solve this quadratic equation, we have to use our good friend, the quadratic formula. Hopefully you remember. If not, write this down. Negative b plus or minus the square root of b squared minus 4ac minus 4ac all over 2a. That's our quadratic formula. Remember what is a, what is b, and what is c of the quadratic equation. Go ahead and plug these values into our quadratic formula. Please, please, please do not start simplifying until you've entered in all of the information already, because that is where many students start making mistakes. Now I'm going to simplify. Opposite of negative 2, positive 2. Negative 2 squared is 4. Minus 4 times 3 is 12. 12 times 4 is 48. All over 6. Going up top. X equals 2 plus or minus the square root of negative 44 divided by 6. And again, I'm going to pull out that negative by turning it into an I. And now I have the square root of 44 divided by 6. Well, 44 is not a perfect square, so let's think. What two numbers multiply to 44, but one of them being a perfect square? Hopefully, you thought of 4 and 11. Square root of 4 is 2, so I have 2 plus or minus 2i times the square root of 11 divided by 6. Now we can take this one step further. So hopefully you've been following along, because I am going to have to do some erasing. So in this video, notice that in my numerator, I have 2 plus or minus 2i divided by, or times the square root of 11 divided by 6. Well, the 2 and the 2i are both even numbers, and so is that 6 in the denominator. So I can actually reduce it a little bit more, but by dividing everything by 2. So I end up with 1 plus or minus 1i times the square root of 11 divided by 3. Ladies and gentlemen, here are just 2 more examples that I'd like you to try on your own. Simplify and see if you can answer. We are going to go over the answers tomorrow, or not tomorrow, I mean on Monday in class. Enjoy your weekend. Your homework assignment is found in Google Classroom.